Welcome to this presentation on feedback control systems. I'm Rajanikant A. Metri from the Department of Electrical Engineering at Rajaram Bapu Institute of Technology, Rajaramnagar. This institute is an empowered autonomous institute approved by AICTE and affiliated with Shivaji University Kolhapur. Throughout this session, I will guide you through the fundamental concepts and applications of feedback control systems, which are essential in engineering and automation. Feel free to reach out to me via email or phone if you have any questions as we go along. Let's get started. Here we focus on control system engineering, which is a vital discipline in modern technology. Control systems are all around us. They help regulate everything from household appliances to complex industrial processes. The key idea is to design systems that behave in a desired way, often by automatically adjusting their actions based on feedback. This ensures stability, accuracy, and efficiency in operations. As we explore this topic, we'll delve into how control systems are analyzed, designed, and applied to solve real-world problems effectively. After completing this session, students will be able to represent physical systems through mathematical models. This is a crucial skill as it allows us to move from real-world scenarios to a form we can analyze and work with mathematically. They will also learn to calculate time domain specifications for second-order systems. Understanding these specifications is essential because it helps us predict how a system responds over time, which is key in control engineering. Additionally, students will develop the ability to analyze different systems using both time domain and frequency domain tools and techniques. This dual approach provides a comprehensive understanding of system behavior from different perspectives. We'll also cover the comparison of various controllers and compensators used in control systems, enabling students to choose the most suitable methods to achieve desired performance. Finally, students will apply state space techniques to analyze and understand MIMO, or multiple input multiple output, systems. This advanced approach is vital for managing complex systems with multiple variables. Overall, these outcomes equip students with a solid foundation in feedback control systems. On this slide, you can see the detailed course content outlined in 3 main units. The first unit introduces the fundamental concepts of control systems, explaining their importance and breaking down the typical components through block diagrams. It also highlights real-world industrial control examples and introduces sensors, actuators, and the difference between open-loop and closed-loop control systems. Moving on to the second unit, we focus on control system representation. This includes understanding transfer functions and the significance of poles and zeros. We'll also explore how to mathematically model simple mechanical, electrical, thermal, and hydraulic systems. Additionally, this unit covers block diagram representation and reduction techniques, along with signal flow graphs and Mason's gain formula, which are essential tools for analyzing complex systems. Finally, the third unit dives into time domain analysis. Here, we study the time response characteristics of first and second order systems, assess steady-state error, and discuss system types. We'll also look at how parameters affect both open and closed loop responses, the concept of sensitivity, and how feedback influences system stability and disturbance rejection. Each of these units is allocated 6 hours, ensuring a thorough understanding of these foundational topics in control systems. Now, let's focus on Unit 2, which covers control system representation. This section is fundamental because it lays the groundwork for understanding how control systems are modeled and analyzed. We'll explore different ways to represent control systems, including mathematical models and graphical tools. This will help us to better predict how a system behaves under various conditions and design effective controllers. Understanding these representations is crucial for working with more complex systems later on. By the end of this chapter, you will be able to clearly define and interpret what a transfer function means in the context of a linear time invariant system. You'll also learn how to identify the poles and zeros of a system, which are crucial for understanding its behavior. We will explore how to develop mathematical models for different types of systems, including electrical, mechanical, thermal, and hydraulic ones, using standard physical laws. Additionally, you'll gain the skills to construct and simplify block diagram representations of control systems, utilizing block diagram algebra for easier analysis. We'll also cover how to create signal flow graphs from system equations or block diagrams, and apply Mason's gain formula to find the overall transfer function. Finally, you'll analyze how the locations of poles and zeros influence system behavior, especially regarding stability and transient response, in a qualitative way. These outcomes will give you a solid foundation to approach control system analysis confidently. Here, we're focusing on some fundamental concepts that form the backbone of system analysis. First, we'll look at the transfer function, which is a crucial tool for describing the input-output relationship of a system in mathematical terms. Alongside this, we'll explore poles and zeros, which help us understand system behavior, stability, and response characteristics. Next, we'll delve into the mathematical representation of various simple systems, whether mechanical, electrical, thermal, or hydraulic. This will give us the ability to model real-world systems in a unified framework. Following that, we'll examine block diagram representation, which is essential for visually mapping out complex systems. We'll not only learn how to construct these diagrams but also how to simplify or reduce them, making analysis more manageable. Lastly, we'll cover signal flow graphs and Mason's gain formula, powerful techniques for analyzing system behavior and determining the overall transfer function in a more systematic and often simpler way. These concepts together will equip us with a solid foundation for deeper system analysis. Here we have the introduction to the Laplace transform, which is a powerful mathematical tool used to represent systems, especially in engineering and control theory. Essentially, the Laplace transform helps us convert complex differential equations, which describe system behavior in the time domain, into simpler algebraic equations in the frequency domain. This transformation makes analyzing and designing systems much more manageable. Understanding this concept is fundamental because it lays the foundation for how we model and control dynamic systems effectively. Today, we're taking a closer look at the Laplace transform. This is a powerful mathematical tool that simplifies the process of analyzing complex systems, especially in engineering and physics. By transforming functions from the time domain into the S-domain, it makes solving differential equations much more manageable. Understanding the Laplace transform is essential because it allows us to work with algebraic equations instead of differential ones, making it easier to design and analyze systems. Throughout this review, we'll cover its definition, key properties, and some important applications. This foundation will really help when we move on to more advanced topics later on. Here, we're focusing on the concept of the transfer function. Essentially, the transfer function is a mathematical representation that defines the relationship between the input and output of a system. It provides a way to analyze how signals are transformed as they pass through the system, often expressed in terms of frequency response. Understanding this function is crucial because it allows us to predict system behavior, design effective filters, and ensure stability in control systems. As we move forward, keep in mind that the transfer function forms the foundation for many advanced topics in system analysis and design. Here, we're focusing on understanding how to find the transfer function. The transfer function is a fundamental concept in control systems and signal processing, as it describes the relationship between the input and the output of a system in the Laplace domain. Essentially, it helps us understand how the system responds to different inputs. In this example, we'll work through the process of calculating the transfer function step by step, breaking down the components involved. This will give us a clear picture of how to represent the system mathematically and analyze its behavior. The transfer function is typically expressed as a ratio of output to input, making it a powerful tool for designing and assessing system performance. Now, we will build on the previous example where we found a certain result, and use it to determine the system's response, C of t, to a specific input, particularly, the unit step function, R of t equals U of t. It's important to note that we are assuming zero initial conditions here, which simplifies our calculations. This process essentially involves applying the transfer function to the input to find the output. By doing this, we can see how the system behaves over time when subjected to a sudden change like the unit step. Understanding this response is crucial for analyzing system stability and performance in practical applications. Let's take a closer look at the pole zero concept, which is fundamental in understanding the behavior of many systems, especially in signal processing and control theory. The pole zero plot is a graphical representation that shows the locations of poles and zeros of a system on the complex plane. Poles are points where the system's transfer function goes to infinity, and they heavily influence system stability and response. Zeros, on the other hand, are points where the transfer function becomes zero, and they affect the frequency characteristics of the system. By analyzing the distribution of poles and zeros, we can predict how the system will behave in terms of stability, resonance, and filtering properties. This plot serves as a valuable tool in designing and analyzing systems to achieve desired performance. Here, we focus on the pole zero concept, which is fundamental in understanding system responses. The key idea is that the form of a system's homogeneous response is directly determined by the locations of its poles on the pole zero plot. Poles are specific points in the complex plane that represent the system's natural frequencies and damping characteristics. When we look at this plot, each pole influences how the system behaves over time, shaping the overall response. This concept is crucial for analyzing stability and dynamic performance, as it links the system's mathematical model to its physical behavior. By studying the pole zero configuration, we can predict how the system will react to different inputs and design it for desired characteristics. Now, let's take some time to work through an example together. This activity is designed to help you apply what we've covered so far. I'll give you 5 minutes to solve the problem. Don't worry about getting it perfect on the first try, the goal here is to practice and deepen your understanding. Feel free to ask questions if anything isn't clear. Ready? Let's get started. Here, we focus on how the locations of poles and zeros influence the behavior of a system. The position of a pole is crucial. The real part corresponds to exponential behavior, which affects how quickly the system's response grows or decays. Meanwhile, the imaginary part is connected to sinusoidal components, influencing oscillations in the system. When we add poles to the transfer function, this tends to pull the root locus towards the right-hand side of the complex plane, which reduces stability and can lead to instability if not managed carefully. Conversely, adding zeros tends to pull the root locus to the left, enhancing stability. Understanding this interaction between poles and zeros helps us predict and control system behavior more effectively. Here, we are looking at the transfer function and its associated poles and zeros. The transfer function characterizes how the system responds to different inputs. Specifically, this system has one real zero located at s equals -1/2. Zeros are important because they indicate the frequencies where the system output is zero, effectively cancelling certain inputs. In addition to this zero, there are two real poles, situated at s equals -3 and s equals -2. Poles are critical as they determine the system's stability and dynamic behavior. The position of these poles and zero tells us a lot about how the system reacts over time. In this case, since all poles and the zero are real and negative, the system is likely stable, with responses that decay rather than grow. Understanding these locations helps us predict and design the system's performance effectively. Let's take a closer look at electrical network transfer functions. The equivalent circuits we're dealing with are made up of three key passive linear components: resistors, capacitors, and inductors. Each of these components has distinct electrical properties and relationships between voltage and current. For resistors, the voltage across the component is directly proportional to the current flowing through it, following Ohm's law. Capacitors, on the other hand, relate voltage to the charge stored, and their current depends on the rate of change of voltage. Inductors link voltage to the rate of change of current through them. Under zero initial conditions, these relationships allow us to model the behavior of complex circuits by analyzing these basic building blocks. This table here neatly summarizes these relationships, making it easier to understand how voltage, current, and charge interact within each component. Understanding these fundamentals is crucial for analyzing and designing efficient electrical networks. Here, we're focusing on an example that helps us understand how to derive the transfer function of an electrical network. Specifically, we want to find the transfer function that relates the capacitor voltage, denoted as Vcs, to the input voltage, Vs. This means we're looking at how the voltage across the capacitor changes in response to the overall input voltage applied to the circuit. Understanding this relationship is crucial because it tells us a lot about the circuit's behavior in the frequency domain, which is essential for analyzing and designing electrical systems effectively. As we proceed, pay close attention to how the voltages and impedances interact, as this will guide us in setting up the right equations to find the transfer function. On this slide, we are focusing on electrical network transfer functions, which are essential for analyzing how different components affect signals within a circuit. The key elements here are the resistor, the inductor, and the capacitor. Each of these components has its own transfer function, which basically describes how they respond to electrical inputs, especially as frequencies change. For example, resistors have a straightforward transfer function as they oppose current consistently, regardless of frequency. Inductors, on the other hand, oppose changes in current more at higher frequencies, and capacitors do the opposite, allowing more current at higher frequencies. Understanding these transfer functions is crucial for designing and analyzing circuits for filtering, signal processing, and many other applications. Now, let's focus on this example where we need to find the transfer function between I2 of S and V of S. Essentially, we're looking to express the output current I2 in terms of the input voltage V in the Laplace domain. This involves analyzing the circuit to relate these two variables, typically by applying circuit laws and using techniques like mesh or node analysis. The transfer function will help us understand how the system responds to different input signals, which is crucial for control and signal processing applications. Here, we're looking at an inverting operational amplifier, which is a fundamental configuration used to implement various transfer functions in electronics. Essentially, this setup allows us to take an input signal and produce an output that is inverted and scaled, based on the resistor values in the circuit. This is crucial for applications like signal processing where precise control over the signal's amplitude and phase is required. By carefully choosing the feedback and input resistors, we can tailor the amplifier's behavior to achieve the desired mathematical operation. This makes inverting amplifiers incredibly versatile components in both analog circuit design and practical systems. Here, we have a non-inverting operational amplifier, which is set up to perform a specific transfer function. The key thing to know about this configuration is that the input signal is applied to the non-inverting terminal, meaning the output signal maintains the same phase as the input. This setup is widely used because it offers high input impedance and low output impedance, which is excellent for signal amplification without loading the source. Essentially, it's a reliable and efficient way to achieve precise signal amplification, making it fundamental in many electronic circuits. Here we have an important topic in operational amplifier circuits, the inverting and non-inverting configurations. These two fundamental setups define how the input signal is processed and amplified by the op-amp. In the inverting configuration, the input signal is applied to the inverting input terminal, which results in the output being inverted in phase, meaning it flips upside down relative to the input. This allows for precise gain control using feedback resistors. Meanwhile, the non-inverting configuration applies the input signal to the non-inverting terminal, so the output remains in phase with the input. Both configurations are widely used in different applications depending on whether we want the output to be a mirror image or to maintain the original signal direction. Understanding these configurations is essential for designing circuits with the desired amplification characteristics and signal behavior. In mechanical systems, much like electrical networks, we work with three fundamental passive components. Two of these, the spring and the mass, are responsible for storing energy within the system. Think of the spring as storing potential energy when it's compressed or stretched, and the mass as storing kinetic energy through its motion. The third component, the viscous damper, acts quite differently. It dissipates energy, usually in the form of heat, which helps to control and reduce oscillations or vibrations within the system. Understanding how these elements interact is crucial when we analyze translational mechanical system transfer functions, as these relationships govern the system's overall behavior and response to external inputs. It seems this slide is currently blank or contains placeholder text without specific content to discuss. If there is intended information or data for this slide, please provide it so I can help you with a detailed narration. Otherwise, we can proceed to the next slide. When dealing with rotational mechanical systems, the approach is very similar to that used for translational mechanical systems. The main difference lies in the quantities involved. Instead of force, we use torque, and instead of translational displacement, we focus on angular displacement. Essentially, the transfer functions for these systems express how the rotational input, measured as torque, relates to the output, which is the angular position or velocity. Understanding this substitution is key to analyzing the behavior of rotational mechanical systems using the same principles we apply to linear systems. This allows us to model and predict system responses effectively in a consistent and unified way. On this slide, we focus on determining the transfer function for a rotational mechanical system. Specifically, we want to find the ratio of the angular displacement, θ2 of s, to the input torque T of s. This transfer function is crucial because it helps us understand how the system responds dynamically to various inputs. By analyzing this, we can predict the system's behavior in the frequency domain, which is essential for design and control purposes. The example provided guides us through the process, showing the relationships between torque and angular displacement in the modeling of rotational systems. This forms the foundation for deeper analysis in mechanical vibrations and control engineering. Today, we're focusing on electromechanical system transfer functions. These functions are essential because they help us understand how electrical inputs convert into mechanical outputs in various systems. By analyzing these relationships, we can predict the system's behavior, design better controls, and improve performance. Transfer functions essentially provide a mathematical model that links input signals to output responses, making them indispensable tools in the design and analysis of electromechanical devices. Understanding these functions allows us to work with motors, sensors, and actuators more effectively, ensuring that each part of the system responds appropriately under different operating conditions. Let's explore the concept of electric circuit analogs. Essentially, an electric circuit analog is an electrical circuit that represents a system from a different field, often mechanical or thermal systems. This allows us to use electrical principles to analyze and understand the behavior of these other systems. For example, when developing a series analog, we start with a mechanical system, then identify the electrical representation we want to achieve. Following this, we design the series analog circuit, carefully selecting parameters that correspond to the mechanical system's characteristics. This approach is invaluable because it gives us a practical way to model and study complex systems using well-established electrical circuit theory. Here, we're looking at the concept of electric circuit analogs. Simply put, an electric circuit analog is an electric circuit that represents or models a system from a completely different field, such as mechanics or hydraulics. This allows us to analyze complex systems using familiar electrical principles. On the slide, you can see the development of a parallel analog. Starting with a mechanical system, we identify the desired electrical representation that can mimic its behavior. Then, we construct the parallel analog itself, which is an electrical circuit designed to reflect the mechanical system's dynamics. Finally, we determine the specific parameters for this analog to ensure that the representation is accurate. This approach is particularly useful because it makes solving problems simpler by leveraging electrical circuit analysis techniques. The key takeaway is that by drawing these analogies, we can understand and predict the behavior of different physical systems through the lens of electricity. A block diagram is essentially a visual way to represent the functions performed by each component in a system and to show how signals flow through it. One of the main advantages is that it's quite straightforward to construct these diagrams, even for complex systems. This simplicity helps us break down and understand how each part contributes to the system's overall operation. Another key benefit is that we can study both the performance of individual components and the system as a whole by using transfer functions, which are clearly laid out in the diagram. This makes analyzing the system much more manageable. Additionally, calculating the overall closed-loop transfer function becomes easier with block diagram rules, giving us a clear view of the system's behavior under feedback conditions. Lastly, the function of each element is easier to visualize, so we can quickly grasp how the entire system operates at a glance. Here, we are focusing on the basic elements of a block diagram. One of the key components is the block itself, which represents a system or a process. Another important element is the summing point, which combines multiple inputs, often by adding or subtracting them. Lastly, the takeoff, or pick-off point, is where we extract a signal or value from the system for feedback or further processing. Understanding these core elements helps us interpret and design block diagrams effectively. Here we have a block diagram illustrating a fundamental electrical circuit. The key components shown are the resistor, denoted as R, and the capacitor, denoted as C. Together, these elements define the behavior of the system. The block labeled GS represents the transfer function, which characterizes how the circuit responds to different input signals in the Laplace domain. This transfer function is essential for analyzing the dynamic performance of the circuit, such as filtering or timing applications. Understanding how R and C influence GS helps us design circuits that meet specific criteria, like controlling the frequency response or adjusting the gain. Although some object types haven't been rendered here, the core concept remains clear. This block diagram simplifies the system into manageable parts for analysis and design. Here, we have the summing point, which is a crucial element in control systems. It's represented by a circle with a cross inside it. This symbol is quite intuitive because it shows multiple inputs coming together at a single point. The summing point takes two or more inputs and produces a single output, which is the algebraic sum of those inputs. What makes it particularly interesting is that it doesn't just add the inputs blindly. Instead, it considers the polarity of each input. This means it can perform summation, subtraction, or even a mix of both, depending on whether the inputs are positive or negative. This flexibility allows us to combine signals effectively, which is essential for accurate system control and analysis. Here, we're looking at the concept of the takeoff point, also known as a branch or pick-off point. Essentially, it's a spot where a single input signal can be split and sent through multiple branches. This means that with a takeoff point, we can feed the same input into one or more blocks or summing points. It's a useful feature for distributing signals efficiently within a system without needing multiple separate inputs. Understanding how takeoff points work is important for designing systems that require signal sharing or parallel processing. Here, we're looking at two fundamental ways to combine blocks in system design: in series, also known as cascade, and in parallel. When blocks are combined in series, the output of one block becomes the input of the next, creating a sequence that the signal passes through step by step. This is useful for processes where each stage modifies the signal before passing it on. On the other hand, when blocks are combined in parallel, the input signal is fed into all blocks simultaneously, and their outputs are then combined. This method allows different operations to be applied concurrently, which can be efficient for certain types of processing. Understanding these combinations is crucial for designing and transforming effective block diagrams in control systems and signal processing. Here, we're focusing on block diagram transformations, specifically moving a summing point in relation to a block. The key idea is understanding how shifting a summing point either behind or ahead of a block affects the overall system. When we move a summing point behind a block, we're essentially changing the input to that block by combining signals first, then applying the block's function. Conversely, moving the summing point ahead of a block means that each input signal is processed separately by the block before being combined. This transformation is useful for simplifying complex diagrams and can help in analyzing or redesigning control systems more effectively. Understanding these shifts allows us to manipulate and interpret block diagrams with greater flexibility and clarity. Here, we focus on block diagram transformations, specifically the concept of replacing summing points. Summing points are crucial for representing how signals are combined in control systems, but sometimes it's necessary to adjust their placement to simplify the overall diagram. By replacing summing points, we can combine multiple summing points into a single one or rearrange them in a way that makes the diagram clearer and easier to analyze. This approach helps in reducing complexity and streamlining the process of interpreting the system's behavior. Understanding how and when to combine summing points is a key step in mastering block diagram transformations. Let's talk about block diagram transformations, specifically focusing on moving a pick-off point in relation to a block. Firstly, when we move a pick-off point ahead of a block, we are essentially repositioning the point where we take the output from before the signal passes through the block. This can help simplify the system by changing where we measure or extract the signal, often making analysis or design easier. Conversely, moving a pickoff point behind a block means shifting the measurement point to after the signal has been processed by the block. This also affects how the system behaves and can be useful for different analysis techniques. Understanding these transformations is crucial because they allow us to manipulate block diagrams without changing the overall system behavior. This makes troubleshooting and system design much more flexible and efficient. Now let's talk about block diagram transformations, focusing first on the concept of eliminating a feedback loop. Feedback loops occur when the output of a system is fed back into the input, which can complicate analysis. By transforming the block diagram to remove these loops, we simplify the system, making it easier to understand and work with. This process often involves rearranging the blocks and combining gains to represent the system without the feedback loop, which streamlines further analysis or design steps. Understanding how to eliminate feedback loops is crucial for effectively managing complex control systems. On this slide, we're summarizing the key concepts behind block diagram transformations. These techniques are essential for simplifying complex control systems by manipulating and rearranging the blocks to achieve an equivalent but more manageable configuration. The main goal is to make analysis and design more straightforward. We focus on moving blocks before or after summing points and takeoff points, combining series and parallel blocks, and understanding how feedback loops affect the system. By applying these transformations carefully, we can reduce any intricate block diagram into a basic form, which helps in determining overall system transfer functions efficiently. Mastering these transformations is crucial because it forms the foundation for more advanced control system design and stability analysis. Always remember, the integrity of the system's behavior must remain intact while you apply these simplifications. Here, we have an example of block diagram reduction. The key idea is to simplify complex systems by systematically combining blocks to reduce the overall diagram into a single equivalent block. This process makes it easier to analyze the system's behavior. You'll notice the use of series, parallel, and feedback connections represented by plus and minus signs, which indicate how blocks combine mathematically. By carefully following these steps, merging series blocks by multiplying their transfer functions, combining parallel blocks through addition, and handling feedback loops appropriately, we can arrive at a much simpler representation. This method not only streamlines the analysis but also helps us understand the core dynamics of the system without getting overwhelmed by its complexity. Here we have an example of block diagram reduction. This process involves simplifying a complex system by systematically combining blocks to create a more manageable representation. The key goal is to reduce the diagram step by step while preserving the overall behavior of the system. Throughout this example, we focus on recognizing series and parallel connections, as well as feedback loops, and then applying the appropriate reduction rules. By doing this, we can transform a complicated network into a single equivalent block. This approach is essential in control systems engineering, as it helps us to analyze and design systems more efficiently. On this slide, we're looking at an example of block diagram reduction. This process involves simplifying a complex block diagram into a more manageable form without changing its overall behavior or functionality. The goal is to make the system easier to analyze and understand. By applying specific reduction techniques, such as combining series and parallel blocks or eliminating feedback loops step by step, we systematically reduce the diagram. This example demonstrates how each stage transforms the original layout, helping to clarify the relationships between different system components. Understanding block diagram reduction is essential for efficient control system design and analysis. On this slide, we're looking at a block diagram reduction example. The main goal here is to simplify a complex system by systematically reducing its components step by step, making it easier to analyze and understand the overall behavior. By combining blocks in series, parallel, and feedback configurations, we can replace multiple elements with a single equivalent block. This simplification helps streamline calculations and provides clearer insight into how the entire system operates as a whole. Understanding this process is crucial for effective system design and control analysis. On this slide, we have an example of block diagram reduction, which is a crucial technique in control systems and system analysis. The purpose of reducing a block diagram is to simplify a complex system into a more manageable form while preserving its essential behavior. Typically, this process involves combining blocks in series or parallel, and eliminating feedback loops by applying specific rules. By doing this step by step, we can reduce multiple interconnected components into a single transfer function that accurately represents the entire system. Understanding how to perform block diagram reduction allows us to analyze system stability, performance, and design control strategies more effectively. It's a fundamental skill that helps in breaking down complex systems into understandable parts, making system design and troubleshooting much easier. On this slide, we have an example of block diagram reduction. Although some elements aren't displayed fully here, the key idea is to simplify complex block diagrams by systematically reducing them to a single block that represents the overall system transfer function. This process involves combining blocks and simplifying connections step by step, using series, parallel, and feedback reduction techniques. By doing so, we make the analysis and design of control systems much more manageable and clearer. Understanding how to perform block diagram reduction is essential for effectively working with complex control systems. Here, we have a block diagram reduction example. The process involves simplifying a complex network of blocks step by step to make analysis easier. By combining series and parallel blocks, and applying reduction rules, we can systematically reduce the entire diagram into a single equivalent block. This simplification helps us understand the overall system behavior without getting lost in intricate details. It's important to follow each step carefully to ensure the reduced model accurately represents the original system. On this slide, we have a block diagram reduction example. Although some objects are not visible here, the main focus is on simplifying complex block diagrams step by step. The purpose of block diagram reduction is to combine various elements into simpler blocks, making it easier to analyze system behavior. By methodically reducing the blocks, we can find overall system transfer functions or other key parameters more efficiently. It's a fundamental technique in control systems engineering to manage and understand complex system interactions. Here, we have a block diagram reduction example. Although the specific objects are not visible in this slide, the key concept is to simplify complex block diagrams step by step. This process helps us analyze system behavior more efficiently by breaking down complicated connections into more manageable parts. By reducing the diagram, we can identify the overall transfer function or equivalent system representation much more easily. This technique is essential for control system analysis and design. Here we have an example that illustrates the key principles we've been discussing. This example helps to contextualize the concepts and shows how they can be applied in a real-world scenario. By examining this case closely, we can better understand the practical implications and the potential outcomes when these strategies are implemented. Let's take a closer look and break down the main elements to see how they work together effectively. On this slide, we have a simple example to illustrate the concept we've been discussing. The key here is to focus on how the example applies the principles in a practical way, making it easier to understand the real-world impact. By examining this example closely, we can see how the theory translates into action, which helps solidify our understanding. Let's take a closer look and consider how the elements interact within this scenario. Here we have a simple example to illustrate the concept we've been discussing. Although the slide is quite minimal, it serves to highlight the core idea in a straightforward way. Let's focus on understanding the key elements and how they apply in practical terms, ensuring we grasp the fundamental principles before moving on. This example will help to solidify your understanding and prepare you for more complex applications later. Here, we have an example to illustrate the points we've been discussing. Although the slide is simple, it serves as a practical demonstration of the concepts in action. Pay attention to how these elements come together, as this example encapsulates the key ideas we've covered so far. A signal flow graph, or SFG, is a visual way to represent the relationships between the variables in a system. Instead of having to simplify complex equations, we can use Mason's gain formula directly to find the transfer function, which is a big advantage. SFGs are particularly useful because they provide a clear graphical representation of systems made up of simultaneous linear equations. In an SFG, we have nodes and branches. A node represents a variable or a signal point in the system. There are three types of nodes: input nodes, output nodes, and mixed nodes, each serving a different role. Branches are the lines connecting these nodes, and they carry important information like the gain, which is essentially the weight or influence of that connection, and direction, which shows the flow of the signal from one node to another. Understanding these components is key to applying Mason's gain formula effectively and analyzing complex systems with ease. On this slide, we have the title SFG, which stands for Shear Force Diagram. This is a fundamental tool in structural analysis used to illustrate how shear forces are distributed along a beam. Understanding the shear force at various points helps us determine how the beam will react under different loads. It's crucial because it guides the design process, ensuring the structure can safely withstand these forces without failure. Although the slide doesn't provide additional details here, remember that mastering SFGs is key to predicting potential weak points and enhancing structural integrity. Here, we're exploring some fundamental concepts related to signal flow graphs. First, an input node is defined as a node that only has outgoing branches. Think of it as the starting point of a signal. Conversely, the output node is one that only has incoming branches, essentially representing the end point. If a node doesn't meet these strict criteria, we can introduce an extra branch with a gain of 1 to satisfy the condition. Next, we have the term a path. This refers to moving through connected branches following the arrow's direction without visiting any node more than once. A forward path is a specific type of path that links the input node to the output node directly. Then, we come to loops, which are paths that start and end at the same node. If two loops share no nodes in common, they're called non-touching loops, an important concept when calculating overall system behavior. Finally, path gain is the product of the gains along each branch in the path. Understanding these terms is crucial for analyzing signal flow in systems effectively. Here we have a block diagram illustrating signal flow graphs, or SFGs. Signal flow graphs are a powerful visual tool used to represent and analyze the relationships between different variables within a system. They help us understand how signals travel from inputs to outputs through various interconnected components. By using blocks and directed branches, we can map out the entire system's signal flow clearly and efficiently. This approach not only simplifies complex system analysis but also aids in identifying key control points and potential feedback loops. Understanding this diagram is crucial for grasping how the system operates and for designing effective control strategies. On this slide, we focus on SFG, which is an important concept to understand in our discussion. Although the slide appears simple, the key idea here is to grasp the fundamental aspects of SFG. We will explore how it fits into the broader context and why it is essential for our overall topic. Let's keep this concept in mind as it will be a foundation for what comes next. Here we have Mason's gain formula, which is a powerful method for determining the overall transfer function of a complex signal flow graph. The transfer function, denoted as TF, is given by the ratio of the output to input, and Mason's formula provides a clear way to calculate this using loop gains and forward paths. First, delta is a key term here, representing 1 minus the sum of all individual loop gains. But it doesn't stop there. If there are multiple loops that don't touch each other, we add the sum of their gain products. Then we subtract the sum of products of all combinations of 3 non-touching loops, and so on, alternating signs throughout. This alternating series captures the complex interactions between loops within the system. Next, pk represents the gain of the kth forward path, basically the direct route from input to output without cycling back. Lastly, k is quite important. It represents the portion of delta that excludes any loops touching the kth forward path. This allows us to isolate the effective loops that are independent of that specific path. By combining all of these elements, pk, k, and delta, we can accurately compute the overall transfer function, even in systems with multiple loops and forward paths. This formula is essential in control systems and signal flow analysis for simplifying and solving complex networks efficiently. Here, we are focusing on Mason's gain formula, specifically looking at an example to understand it better. One of the key steps in applying this formula is to identify all the possible forward paths within the system. So, the big question we're asking here is, how many forward paths can we find? Recognizing each forward path is crucial because it helps us calculate the overall transfer function accurately. Let's take a moment to carefully examine the system to pinpoint every forward path from the input to the output. Here, we're looking at an example of Mason's gain formula. The key concept to understand is how we identify all the individual loops within a signal flow graph. These loops are essential because they help us calculate the overall transfer function of the system. By carefully listing every possible loop, we can apply Mason's gain formula accurately to determine the system's gain. This step is crucial as missing any loop can lead to incorrect results. So, the focus here is on thoroughly finding all the loops before proceeding with the formula. Here, we're looking at an example related to Mason's gain formula, specifically focusing on non-touching loops. Non-touching loops are pairs of loops that do not share any common nodes. In this case, we have only one such pair, which are loops L1 and L3. When these loops are non-touching, their gains can be multiplied together to contribute to the overall gain calculation. For this pair, the product of their gains is given as negative G2 times G3 times G4 times G5. Understanding these pairs is crucial because it helps us systematically determine the determinant in Mason's formula, making the analysis of complex systems more manageable. Now, let's take a closer look at Mason's gain formula with an example. To find one, the key step is to set the gains of all branches that touch the forward path P1 to 0 in the equation for delta. This effectively removes those paths from consideration, allowing us to focus specifically on the loops that do not intersect with P1. By doing this, we can accurately calculate the determinant corresponding to that forward path, which is essential in analyzing complex control systems. This method ensures we account for all interactions within the system, making our overall analysis precise and reliable. Now, to find 2 using Mason's gain formula, we need to look at the forward path P2. The key step here is to make the gains of all branches that touch this forward path equal to 0. In this case, the branches G1, G4, and G5 all touch the forward path P2, so we set their gains to 0 in the equation. On the other hand, gains G2 and G3 do not touch the forward path P2, so we keep them as they are. This approach helps us isolate the effect of the non-touching loops and accurately calculate 2. Here, we're looking at an example that demonstrates Mason's gain formula. This formula is a powerful tool we use to determine the overall gain of a complex system by analyzing its signal flow graph. Instead of going through numerous algebraic steps, Mason's gain formula simplifies the process by considering all the forward paths and loops in the system and their interactions. Understanding this example will help you clearly see how to apply the formula to find the transfer function, which represents the system's output response to an input. This method is especially useful in control systems and signal processing where systems can have multiple feedback loops. As we walk through the example, pay close attention to how the paths and loops are identified and how the gains are calculated and combined. Here we have an example of a signal flow graph or SFG, which helps us analyze control systems. First, let's look at the forward path gains, labeled as P1 and P2, which in this case are ASA and AGH respectively. These represent the paths from input to output without any loops. Next, we examine the 4 individual loops present in this SFG. Each loop has a gain associated with it. L1 is BC, L2 is EHD, L3 is F, and L4 is GHDB. These loops represent feedback paths that affect the overall system behavior. Importantly, we also identify non-touching loops, which don't share any common nodes. Here, the only possible combination of such loops is L1 and L3, whose combined loop gain product is BCF. Now, looking at the determinant terms, 1 and 2 are both equal to 1 because all loops touch the respective forward paths P1 and P2. The overall determinant is calculated by subtracting the sum of the loop gains from 1, and then adding back the gain product of the non-touching loops. So, equals 1 minus the sum of BC, EHD, F, and GHDB, plus BCF. All these elements come together in the transfer function, which quantifies the relationship between input and output in the system, taking into account these forward paths and loops. This approach allows us to systematically analyze complex systems with multiple feedback mechanisms. Here, we're looking at examples involving signal flow graphs, focusing particularly on non-touching loops. We have two individual loops identified as L1, which is G1H1, and L2, which is G6. These loops don't touch each other, so their product forms one non-touching loop combination, L1L2 equals G1 G6H1. Next, we note that the determinants for the system, 1, 2, and 3, are all equal to 1 because every loop touches all three forward paths, P1, P2, and P3. The overall determinant is calculated with the formula 1 minus the sum of the individual loop gains, which in this case is G1H1 plus G6, plus the product of the non-touching loops G1 G6H1. Finally, there are three forward paths in the graph. Their gains are given as P1 equals G1 G2 G3, P2 equals G4 G3, and P3 equals G5. Understanding these relationships helps in applying Mason's gain formula to find the overall system gain efficiently. On this slide, we are focusing on examples of SFGs, or signal flow graphs. Signal flow graphs are a powerful visual tool used to represent the relationships and dependencies between variables in a system. By exploring various examples, we can better understand how these graphs simplify complex mathematical equations and system behaviors into a clear, graphical format. This not only helps in analyzing the dynamics but also makes it easier to apply methods like Mason's gain formula to find system responses efficiently. As we go through the examples, pay attention to how nodes and directed branches illustrate the flow of signals and how feedback loops are represented. This foundational understanding is crucial for working with control systems and signal processing applications. Now, let's look at some examples involving signal flow graphs. We start with forward path gains, which represent the gain from the input to the output along a particular path. Then, we consider individual loop gains, which are the gains around feedback loops within the system. In this example, loop L1 does not intersect with loop L2, so the overall determinant delta is calculated accordingly. Specifically, both 1 and 2 are equal to 1, indicating no interaction or overlap between these loops. However, for loop L3, the determinant is expressed as 1 minus L1, reflecting the influence of the first loop on this part of the system's behavior. Understanding how these determinants are derived and how the loops interact is crucial for analyzing complex feedback systems effectively. This approach helps us quantify the combined effect of multiple loops and paths within the system. On this slide, we focus on examples related to signal flow graphs, or SFGs. First, we have forward paths, which represent the routes through the system from input to output without any direction reversals. Understanding these paths is essential because they help us analyze how signals propagate through the system. Next, we look at individual loop gains, which quantify the feedback within each loop. Each loop gain gives us insight into how much influence a feedback loop has on the overall system behavior. Finally, we consider combinations of two non-touching feedback loops. These are loops that operate independently without sharing any nodes, and recognizing these combinations is crucial when applying Mason's gain formula to find the overall system transfer function. Keeping track of these elements helps us systematically study complex control systems with multiple feedback loops. Here are the key references that have informed our presentation. The primary textbook, Control Systems Engineering by Norman Knies, provides a solid foundation in control theory and practical applications. For industrial insights and examples, we looked at resources discussing industrial control systems, including their types and the concept of automation. Mohammed Sawar's article on Medium offers a comprehensive introduction to control systems, which helped clarify many complex ideas. Additionally, Acrome Robotics' explanation of control engineering gave us a modern perspective on the field. Lastly, the Joe VE video linked provides a visual demonstration that complements our theoretical understanding. These references together ensure that our content is both accurate and up to date. Here we have a summary of the questions along with their respective course outcome mappings. It's important to note how the questions are aligned with specific learning objectives. Questions 1 through 5 are focused solely on course outcome 1, which indicates that this area is fundamental to the material covered. Then, questions 6 to 11 incorporate both course outcome 1 and 3, showing a blend of concepts from these two outcomes. This mapping helps ensure that the assessment is directly tied to the key learning goals and provides a clear framework for evaluating understanding and progress. If you have any questions about how these mappings relate to the course objectives, I'd be happy to clarify. Thank you all for your time and attention. I really appreciate your engagement throughout the presentation. If you have any questions or would like to discuss anything further, please feel free to reach out. Thanks again.